into this house. It contains a very beautiful tiling. So, okay, but tilings are used, nowadays for decoration, but in fact, they have been used already since antiquity. And so here are a few pictures. This comes from, so this is a Greek mosaic, I believe, that comes from Arikanda, which is nowadays in Turkey, but already comes from the ancient Greeks. This is in Pompeii in Italy, so I visited Pompeii recently. And I was really amazed by the beautiful geometric patterns that they had in the houses. So as you know, Pompeii was destroyed by the eruption of a volcano in 79 after Christ. So it means that all these beautiful art designs were made before that period, right? So this is very nice. Another extremely nice thing is the Alhambra Palace, which you might know, in Spain. So I think the palace was built in the 8th century, but then it was vaguely destroyed and rebuilt, so maybe these mosaics are more from the 13th century, but still they're very beautiful. In the Alhambra, what is very remarkable is that you can find all the possible sorts of tilings in the plain. So this is one other example. This is yet another example. And then people have been continuing to use these tilings even in architecture. So this is the famous marble courtyard in Versailles. And even very recently, so in Mexico, so this museum that was built only 6 years ago. So what I want to do in this talk is talk about tilings as mathematical objects. So what is a tiling? So what I will call tiling of Rn is a collection of compact subsets of Rn, which I want to call the tiles, and that satisfy some very natural properties. So the first property is that the collection of all the tiles should cover Rn, and the interiors of the tiles should be disjoint. And then there's a local finiteness condition, which means that not infinitely many tiles cannot accumulate at a given spot, right? So if you take any compact subset of Rn, it will meet only finitely many tiles. So here are some examples, and I drew some colors, but this is just to make it beautiful. We will not count colors as meaning anything in this talk. So here you see, this is one tile, this is another tile, so there are many little tiles that are squares. But it's possible that there are several types of tiles, like this one. It has both squares and little triangles. So, okay. And often, as in these examples, the tilings may have symmetries. So what is a symmetry? Well, a Euclidean symmetry of the tiling is just a Euclidean transformation of Rn that preserves the tiling, which means if you take a tile, its image by the symmetry is a tile. So possibly a different tile or possibly the same tile. Okay, so for instance, here you see this one has many, many symmetries. So like translation, okay, maybe I should first recall what a Euclidean transformation is. So essentially a Euclidean transformation, you're allowed to do translations, and then you're allowed to do orthogonal transformations, so essentially rotations. So that's a Euclidean transformation, and so these Euclidean symmetries are supposed to be just the Euclidean transformations that preserve the tiling. So let's go back to this one. This one has many symmetries, like it's invariant under translation by one to the right, translation by one upwards, downwards, to the left. You can also do some mirror symmetries along a line. So either one of the black lines, or you could take like the line in the middle that goes in the middle of the tiles. You could also do a mirror symmetry along this. Or you could also do a mirror symmetry along this, or you could do some central symmetries. So you see that there are many symmetries, right? And the nice things about symmetries is that when you have two symmetries, you can do one and then do the other and compose them, and you get another symmetry. So it's some kind of multiplication of the symmetries. And also when you do one symmetry, you can kind of undo it, so do its inverse. And then there's a neutral element, so something that does nothing, and we still want to call it a symmetry for some reason, which is just the identity of Rn. So this means that these symmetry trees form an algebraic structure which is called a group, right? Something where you have multiplication, inverse, and some neutral element. And historically, in fact, the notion of group very much originated from looking at symmetries like this and composing them. So in this talk, I will always assume that all my tilings are periodic. So this means that they contain enough symmetries, or more precisely, that you can start with finitely many tiles, and then you obtain all the other tiles by applying symmetries. So in these three examples, you can just start with one tile and apply all the symmetries. In this example, you can start with one square and one triangle, and then if you apply all the symmetries, you obtain all the tiles. Okay, so I should mention that, and I will call it a Euclidean tiling because it's Euclidean transformations. So I should mention that there exists tiling that are not periodic. So this is the famous Penrose tiling, and maybe you think that it has some periodicity because you think that you recognize some pattern, but in fact, if you look very carefully, for instance, okay, maybe I think this tile is very much similar to this one because I could apply some Euclidean transformation, but if I look then at some other spots here in the tiling, I see that it's not preserved by this Euclidean transformation. So it is not periodic, and there's a lot of modern mathematics that studies non-periodic tilings, and it's very interesting, but in this talk, I will not look at this at all. So, sorry, I hope it will still be a little bit interesting. So we will just look at like the classical things, the periodic tilings. Okay, so the thing is, so we have a tiling, it is periodic, and it has symmetries that form a group, and this group is usually called a crystallographic group. And this is for historical reasons, because the study of these groups is very much linked to the study of arrangements of crystals in a three-dimensional space, like these. Okay, so now we would like to classify tilings. So we would like to say when two tilings are equivalent, so that there's a chance that we can actually classify them. So we want to say that they are equivalent if essentially they have the same symmetries, which means that their symmetry groups are isomorphic. So, for instance, we want to say that these two tilings, although they look quite different, right? But we want to say that they are equivalent because their symmetry group is generated by two linearly independent translations. So here I said the colors don't matter. So here it's generated by the translation, the horizontal translation that sends the little red winged horse to the white one, and then here. And then it's also generated by the upwards translation. And here it's generated by translation in this direction and translation in this direction. So the symmetries are the same, therefore we say the tilings are equivalent. But here's another tiling, and this one we do not want to say that it is equivalent at all, because this one has more symmetries than that one. So if you look at the symmetry group of this one, it includes two linearly independent translations, so namely here horizontally, and maybe in this direction. But also it includes here, you see the two lizards that meet by their tongues, or mouth. Here they differ by a central symmetry. And here we do not have any central symmetries. So these are not equivalent. So the goal is now to classify these tilings, and this has been done in small dimension. So, and people have given the tilings some names. So for instance, so this tiling, its symmetry group is called P3, and so I don't know why they always start by P, but 3 means that if you look at the rotations, I mean the symmetries of the tiling that are rotations, well, you have some that have angle 2 pi over 3 and 4 pi over 3, and then you have the 6 pi over 3, so which is the identity. So the smallest possible angle of a rotation that preserves the tiling is actually 2 pi over 3. And this 3 explains why it's called P3. And there are no mirror reflections. This one, on the other hand, at this point you see that there are rotations of angle 2 pi over 6 that preserve the tiling. So it's called P6, and then there's a little n because there are mirror reflections. And then this one is called the P4G because the smallest rotation angle is 2 pi over 4. There are mirror reflections, and there are also glide reflections. So a glide reflection is you compose some mirror reflection with some translation. So, yeah. So anyway, the goal has been, and this has been going on for many decades, to classify those tilings, at least in small dimension. And it is actually possible, and the reason why it's possible is a theorem of Bieberbach from about 100 years ago that says that if I fix the dimension n, then there are only finitely many Euclidean tilings of Rn up to equivalence. And so people have been classifying them and counting them, and you see in dimension 2 there are 17 of them, which is already quite a large number, but for 3, n equals 3, it's only 219, and then it grows extremely quickly, and in dimension 6 you have more than 28 million. So I think dimension 7, they have not been classified, because the number would maybe be too big, I don't know. Okay, and so how does the classification go? How can we possibly classify the tilings? Well, the very useful theorem here is again by Bieberbach, and it says that the symmetry group of a Euclidean tiling of Rn is essentially a group of translations generated by n linearly independent translations. So by essentially, I mean up to finite index. So which means that there's a finite set of symmetries such that if you compose by this finite set, you get always one of those translations in this group, isomorphic to Zn. And so then the idea to do the classification is you know that your symmetry group must contain a group of translation isomorphic to Zn, so you start from this, and then you try to add finitely many symmetries and Euclidean transformations and see if this can be or not the symmetry group of a tiling. So you just explore all possibilities and you see what can happen. Okay. So for instance, so this one, as I said, the symmetry group is exactly Z2, and here the symmetry group, you need to extend Z2 by this central symmetry here. Okay. So now what I would like to do in the rest of the talk is to talk about a slightly more general type of tiling, namely not only Euclidean tilings, but also affine tilings, which are a bit more general. So the idea is now, instead of just allowing for symmetries that are Euclidean transformations, we will allow for symmetries that are affine transformations. And so maybe I should just recall what an affine transformation is. So it's a little bit like before. You're allowed to do translations and rotations, but you're also allowed more. So you're allowed to do homothéses, so namely expand, like this. Oops, what happened? Sorry. Which one? Sorry. Okay, and okay, but you're also so you're allowed to do homothéses, but then the main difference is that you're allowed to do shearing. So just things like that change your flag like this, or even more like this. Okay, and so an affine transformation is basically a combination of all these possibilities. So, yeah. So now an affine symmetry of the tiling is an affine transformation that sends tile to tile, and again these symmetries form a group, and we want to call it an affine crystallographic group. So, and I should insist again that the main difference is that you allow for shearing. And again, we will always assume that the tiling is periodic, which means, again, that there are only finitely many tiles modulo the symmetries, and we will call it an affine tiling. Okay, so maybe some examples to make things more concrete. So here's a classical example that's Euclidean, and you see that the symmetry group is generated by two linearly independent translations, one that just moves by one to the right horizontally, that's A, and then B is the one that moves by one that moves in this direction, right? So that's a very classical tiling, but now here's a less classical tiling, which is affine but not Euclidean. So it's this one. So you see, what are the symmetries? Well, you still have the translation by one to the right, this is A, but now you also have this transformation B, which is not a translation, because it has a non-trivial linear part here. And what it does is, so for instance, let's say we start with this little white tile. What does it do to it? Well, first it shears it to the right, and then it moves it up by one. So it moves the white into this red thing. Then if you would apply B again, you would shear again to the right and move up. So you would get this one, and then you would get this one, etc. So this is a less classical tiling that's affine but not Euclidean. And now we can also see in dimension 3. So I tried to draw pictures in dimension 3, but it's not so easy. So I hope you kind of see something. This one is a Euclidean tiling, again, very classical, generated by three translations, by one to the right, by one towards the back of the screen, and by one towards the ceiling, right? But now this one is an affine tiling that's not Euclidean, and the symmetry group is generated by translation by one to the right, translation by one towards the screen, and this affine transformation that's not a translation, and because of this linear part. And what it does is, let's say you take this little, or let's say this pink tile, and what it does, it first shears it to the right and then moves it up. So it moves it, in fact, to this tile. And again, it will move to this tile, etc. And so you get this interesting tiling. Okay, so now what we would like to do is, I explained before some theorems about Euclidean tilings, and now what we want to do is try to see to what extent they generalize to all affine tilings. So the main thing that I explained before was this theorem of B-Barbach, these two theorems of B-Barbach. The first one that said that there were only finitely many Euclidean tilings of Rn up to equivalence, which was great because we could have hoped to classify them. And then the one that said that essentially the symmetry group was Zn. So let's see what happens in the affine case. So there's good news and bad news. The good news is that in dimension 2, there are also only finitely many affine tilings of R2 up to equivalence, which is nice. But unfortunately, for n at least 3, there are infinitely many. So this makes things more difficult. And then, what about the second B-Barbach theorem? Well, so first of all, the answer is not known. It's only a conjecture. And the conjecture says, well, the symmetry group of an affine tiling of Rn is not always Zn, but it's very close to being Zn. So it's essentially an n polycyclic group, which means that it's an extension of Z by Z by Z by Z by Z n times, but extension is not necessarily a direct product. So it's just slightly more complicated, but still in the same spirit. For instance, in this three-dimensional tiling that I showed you before, the symmetry group was actually a semi-direct product of Z2 with Z. So this conjecture is nice. It says that things are slightly more general, but still very similar to the Euclidean case. And it has been proved in dimension at most 6, so only small dimension, but it's wide open in general. So this is pretty amazing. That's this is not known, but yeah, that's the case. So as you see, there are still many things we do not know about affine tilings. But still, today in this talk, I want to, despite the fact that we do not know things, I want to generalize further. So I want to generalize further by looking at affine tilings that now are allowed to have non-compact tiles. So it's easy to construct examples of tilings with non-compact tiles. You can just start with your favorite tiling, like this one, and you can modify it a little bit, and then you get a tiling where the tiles are not compact. Of course, I had to truncate for the picture, but this is supposed to go to infinity here and there, and there, and there. Okay, or you could take this three-dimensional one, and you can also modify it a bit, and then you get tiling with with non-compact tiles. And essentially, when we've done this procedure, what we've done is here we looked at the symmetries and we just decided to forget some symmetries. And so the new symmetry group that we get here is just a subgroup of the initial symmetry group here. And in particular, it is still essentially polycyclic, so it's quite close to being zk for some k less than n. So this is already nice, and so it's very similar to the Arnold conjecture about the case with compact tiles, where as I said, the group was always polycyclic. But Milner in 1977 asked, but is it really the case that all the tilings, all the affine tilings with non-compact tiles will have such a tame, such a very classical symmetry group, so close to being Zn? And it was really unclear for several years what the answer was, until Margulis came in 1983, and he gave the answer that in fact, no. And there exists affine tilings of R3 with non-compact tiles where the symmetry group is a non-abelian free group. And I want to call these tilings exotic. I mean, as you know, in mathematics, sometimes we have very classical situations or objects, and suddenly we find something unexpected or surprising, and then we want to call it like exotic. So that's I want to call them exotic. So, and then the symmetry group is very different from being a polycyclic group. It's in fact a non-abelian free group. So maybe I should recall what a non-abelian free group is. So just to say in one sentence, it's a group where there's no relation whatsoever between the elements. But if I want to make it more precise, so to construct a non-abelian free group, what you do is you take a finite set, which I want to think of as a set of letters or some alphabet with finitely many letters. And then the associated non-abelian free group is just you take the elements of the groups are all the possible words in these letters and the inverses of these letters. And so we do a multiplication to have a group structure. So what's the multiplication is? It's the most natural thing you could think of. Namely, you have one word, you have another word in these letters, you just write one next to the other, so this is called concatenation, and by writing them next to each other, you get a longer word, which is by definition the product of your two elements. Okay, and so maybe I should also mention how to visualize it, because sometimes it helps if you can have a picture to kind of see your group or your object. So here maybe a good picture would be a tree. So I want to see my group as a tree, and here is the identity element of my group, and then here I put A, here I put A inverse, here I put B, and here I put B inverse. And then, so for instance I go A, then the next one will be AB, then this one will be AB, A minus 1, then if I go up again, this will be AB, A minus 1B. So each time, if I go to the right, I add an A. If I go upwards, I add a B. If I go to the left, I add an A minus 1. If I go downwards, I add a B minus 1. So for instance, here is B, and then here is B, A minus 1, and here is B, A minus 1, B minus 1. So you see that this group is actually very different from Zn. It is not at all commutative. For instance, here you have this element B, A minus 1, B minus 1, and it's very different from A minus 1. And if the group was commutative, or abelian, then these would be the same. But here, they are not the same. And so, I mean, maybe one picture you can have in mind is Zn is like an American city. I don't know if you've been to the US, but the cities are like grids. And there are blocks, and if you go one block north and then you go one block east, it's the same thing as if you first went one block east and one block north, right? So that's Zn. But here the situation is extremely different. So you should imagine that, in fact, you're living on a tree, and if you first go north and then east, you find yourself in a totally different place than if you first went east and then north. So that's the picture. So anyway, Margulis constructed those affine tilings of R3 where the symmetry group is such a non-abelian free group. And what I want to do now is try to explain a little bit more about these exotic tilings of R3. So first of all, let me give some brief overview of what happened. So as I explained, Margulis constructed the first examples of such tilings in 1983. But then, 9 years later, Todd Drum, who is an American mathematician, constructed more examples in a very geometric way. And what I want to do now is try to explain to you Drum's construction. And the reason why it's actually maybe good to understand this construction is that, in fact, all exotic tilings of R3 turn out to come from Drum's construction. So all the tilings of R3 where the symmetry group is not essentially polycyclic. Okay, so I'm going to explain Drum's construction. And first, I should explain some very basic principle on how we're going to construct the tiling. So if you want to construct a tiling, one thing you can do is I will restrict to tilings where there's only one tile modulo the symmetries. In general, there could be several tiles modulo the symmetries, but today let's make it simple. So we just say there's one tile modulo the symmetries. So what we can do is we describe one tile very explicitly, and then we describe the symmetries by giving generators for this group of symmetries. And then, how do we obtain the tiling? Well, you just take your initial tile, you apply all the possible symmetries, and you get all the tiles. So maybe just some very simple example in R2. So I want to describe this tiling. So, okay, what I can do is I'm going to describe one tile, namely this one. And I say, okay, this tile is bounded by two pairs of parallel segments. So there is one pair is S1, this little segment, S1 prime is this little segment, then the other pair is S2 is here, and S2 prime is here. And then what are the symmetries? Well, the symmetries are generated by two linearly independent translations. One translation is sending S1 to S1 prime, so it's just a translation by one to the right. The other translation is sending S2 to S2 prime, so it's translation like this. And then, as I said before, the tiling is just you start from this tile, you apply all the symmetries generated by these two translations, and you obtain all the tiles, so the whole tiling. So now we're going to do the same thing, but it will be in R3 instead of R2. And the tiles will be non-compact instead of being compact. But still, you should keep this in mind. We will do exactly something similar. Okay, so there are two ideas. The first idea is, so in my previous two-dimensional example, the symmetries, so the translations, they preserved the Euclidean metric on R2. So now, the symmetries of my tiling of R3 will not preserve the Euclidean metric of R3, but they will preserve some indefinite metric on R3. Namely, so if you recall, how does the Euclidean distance work on R3? You take 2 points, and how do you define their distance? Well, so I take x and y, and then if I want to define the distance between x and y, I should just take the norm of y minus x. And what is the norm? It's the square root of this quadratic form applied to y minus x. So now we do the same thing, except, so instead of having, as in the Euclidean case, x1 squared plus x2 squared plus x3 squared, so this is the classical Euclidean setting, we now have x1 squared plus x2 squared minus x3 squared. And this makes the geometry very different. So I drew a picture. On this picture, you see a cone, and the cone is exactly where the quadratic form Q is 0. And then outside of the cone, the quadratic form is positive, and inside of the cone, the quadratic form is negative. And so now you can define the distance, a distance, a pseudo-distance, it's not really a distance, between any 2 points. But the distance, the sign of the distance will depend on the configuration of the 2 points. So let's say that I move x here to the origin. So 3 things can happen. If y is outside of the cone, then that's great. I'm just in the classical Euclidean setting, and so the distance is just the square roots of q of y minus x. Now, if y is on the cone, then I will say that the distance between x and y is 0. So this is maybe surprising, but I said that d is not really a distance in the usual sense. So you can take 0 values. And then if x is here and y is inside the cone, well, we will say that the distance is negative, and it's minus the square root of minus q of y minus x. So anyway, this defines some other type of geometry on R3, which is often called Lorentzian geometry, and R3 with this Lorentzian flat geometry is sometimes called Minkowski 3-space, but this doesn't matter for today. So my only point is that the symmetries of the tiling will preserve some metric on R3, but which will be indefinite instead of being the Euclidean metric. So that was idea number 1. And now we go to idea number 2. So now idea number 2 was, instead of having, as in my 2-dimensional example, some tiles bounded by segments, the tiles will be bordered by planes that have been kind of twisted and that are called crooked planes. So what is a crooked plane? So that's the picture of a crooked plane. Except I just drew the cone to make it easier to see, but the cone is not part of the crooked plane. So that's the thing, and it has 3 parts. So one middle part here that looks like a bow tie, and which is called the stem. And the stem is just the intersection of the interior of the cone with one plane going through the origin. And then there are 2 other parts, here and there, that are called the wings, and that are half planes. So here we have one half plane that goes on this boundary of the stem, and that's tangent to the cone. And here this is another wing, which is again tangent to the cone and meets the stem in this line. So yeah, I don't know if this is very clear. So also then you're allowed to translate such a crooked plane. So in case it's not very clear, I've actually, unfortunately it's small, but this is a small model of a crooked plane. So you can see that it's actually not exactly the same as on my picture, because you have 2 types of crooked planes. You have those where the wings go to the right, both wings go to the right, but in my model, actually both wings go to the left. So it's just a question of choice. I made a different model, I'm sorry for that. But yeah, so that's the idea. And so now, what we want to do is, what Drum does, more precisely, is that he follows the basic principle. So he first describes one tile, and his tile is bounded by pairs of pairwise disjoint crooked planes. So here was one crooked plane, and you can actually add some other crooked planes in such a way that it's disjoint. So maybe you don't believe me that crooked planes can be disjoint. So in case you don't believe me, I have another crooked plane. And I can try to show you how you can make them disjoint. So we can start with two crooked planes that meet in the origin. And then you see that if I translate one in the correct direction, it's actually, I'm sorry, it's actually getting disjoint. I mean, do you believe me that it can be disjoint? So, yeah, okay, so actually I will show you some more pictures so that hopefully you believe me even more. So this is as before, so we first describe one tile. So the tile, I should insist, I'm sorry, but so these crooked planes, of course I had to truncate them for the picture, but they're supposed to go to infinity upwards and go to infinity downwards, and the wing is a half plane, so it goes to infinity this way, and the other wing goes to infinity that way. So it's really an infinite object, but I'm sorry that I had to draw something finite on the screen. So my tile is what's bounded by these four crooked planes. It's what's inside. So here it goes to infinity, 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 and upwards it goes to infinity and downwards also. So it's really non-compact, right? Okay, so now we describe the symmetries. So the group of symmetries is generated by affine transformations of R3. So it's not translations anymore, but still they send Ci to Ci prime. So you have A1 sends this crooked plane to, so the purple one to the blue one, and A2 sends the red one to the green one. Okay. And then it's as before, what is the tiling? The tiling is you have your fundamental tile here, and then you apply all the symmetries generated by A1 and A2, and what you get is your full tiling. And so, again, I brought another little thing, which maybe is a bit small for you to see, but so this was made by a 3D printer by Bill Goldman in the University of Maryland, and this shows four tiles of such a tiling. So here it's a little bit different. It's bounded by 3 crooked planes, so it's an odd number instead of an even number, but this doesn't change very much. And so you see that, well, you can take out the pieces, and if you like, later you can take a look and see how it looks here. Okay, so, so now I show you maybe some more pictures. So this is just the same thing as this, but I just rotate it so that you see better what's going on. So I'm really not changing anything, I'm just rotating, so that you see that actually, yes, the blue and the purple crooked planes are disjoint, so that's good. And the purple and the red are disjoint, that's good. And you can move it around and you see that in fact, yeah, they're all disjoint. I mean, here you see this one and this one are also disjoint. Okay, and so what I claim is that the group of symmetries generated by A1 and A2 is actually a non-abelian free group. So why is this true? Well, to check this, we can apply some classical dynamical criterion that we use often in geometry, which is called ping pong. So, I mean, you all know ping pong. Ping pong is you have a table and it's separated into two, and you have two players. Two players just send the ball from one side to the other side. And so you just essentially have two regions and a little ball that goes back and forth between two regions. And here the idea is really very similar, except that the ball doesn't just go back and forth between two regions, but between 4 regions in my picture, and in general between an even number of regions that can be larger than 4, maybe. But here it's 4. So I mean, what's the idea? What's the dynamics of A1? A1 sends everything that's on this side, I mean, on the right side of the purple crooked plane, behind the blue crooked plane. And A2 sends everything that's above the orange Crooked plane on the right side of the green Crooked plane. So this is what we will use. So let's check that gamma is a non-abelian free group. So what does it mean that gamma is a non-abelian free group? It means if I take any word in the letters A1, A2, A1 inverse, A2 inverse, this word is non-trivial. Okay? So let's take, for instance, this word. I just picked a random word. So let's check that it's non-trivial. So these letters are going to play ping pong here. So the first player is player A2. And A2, as I explained, it moves the orange Crooked plane to the green Crooked plane, and while moving this, it just pushes everything that's on above the orange towards the green. So I start with here a little ball, a ping pong ball. Well, in mathematics it's a point, but let's just imagine that it's a ball. And A2 pushes it here, right? And then the next player, so now A2 has finished to play for the moment, so the next player is A1. And what A1 does is everything that's on this side of the purple, it moves on that side of the blue. In particular, it moves my ball here. Okay, so now A1 is done, A2 minus 1 can play. So A2 minus 1 moves everything that's on this side of the green towards this side of the orange, so in particular my ball moves here, and then the last player for this word is A1, and A1 moves it here. So I've applied my word, and I started with my ball, which was here, and my ball has gone there. So there's no way my ball has not come back to the same place. So this means this word is not trivial, right? So this shows that no word is trivial. So in particular, if here I took a commutator, I would see that gamma is not commutative, not abelian. But in fact, it works for any word, and this is how I get it, that it's a free group. Okay, so now the thing is that, so we have this very nice construction, and it was conjectured in 1995 that in fact, all the exotic timings of R3 are obtained from Drum's construction with Crooked planes. And it turns out to be true, as it was proved recently. And now I want to explain the idea of why this is true. So, okay, how do we prove the Crooked plane conjecture? So, the main idea is, so we want to do affine geometry in dimension 3. But in order to do this, we are going to use hyperbolic geometry in dimension 2. And this is nice because, first of all, hyperbolic geometry is great. And second of all, 2 dimensions is easier to understand than 3 dimensions, right? Okay, so probably many of you have heard about the hyperbolic plane, which is one of the non-Euclidean geometries. And maybe most of you have heard about the most classical model of the hyperbolic plane, which is the upper half plane. So you just take the complex numbers with positive imaginary parts, and this is your H2 in the hyperbolic plane, and you can put some metric on it so that the geodesics are either going to be the vertical rays like this, or the half circles like this. Okay, and then the isometries are essentially the group PSL2R that acts on the upper half space by homographies, right? Okay, so that's one model which is very well known, but I don't know if you know, I mean there are several models of the hyperbolic plane, and here is another model of the hyperbolic plane which lives in R3, namely this is the quadratic form that we had before. And we just take the points where this quadratic form is equal to -1. So this is a 2-sheeted hyperboloid here and there. And we decide to take only the upper sheet. So we take the third coordinate to be positive. And then the geodesics in this model are just the intersection of the hyperboloid with planes going through the identity. And the isometries now are SO21, which is the subgroup of SL3R, that preserves this quadratic form. So that preserves our indefinite metric that I was talking about earlier. Okay. So now let's go back to our tiling. So we start with some exotic tiling of R3. And the first thing to see, and it was proved by Fried and Goldman in '83, is that exactly as in Drum's construction, your symmetry group must preserve the indefinite metric given by this quadratic form, always. Now this is not too hard to see. So in particular, the linear part of gamma is contained in my group SO21, which was the group that preserves this quadratic form, that preserves the indefinite metric. But, as I explained before, which turned out to be also the isometries of H2. So now that's great. The linear part of gamma is isometries of H2. So if I tell you this, then probably you can believe me that the linear part of gamma in fact defines a non-compact hyperbolic surface. So the point here is just that the projection of gamma onto the linear part is injective and discrete, and therefore this is how it defines a non-compact hyperbolic surface, like this one. And now what about the translational part of gamma? Well, if you really think about what it means, it defines an infinitesimal deformation of my hyperbolic surface. And there's a very nice theorem of Goldman, Labourie, and Margulis that says that in the setting, so we have a hyperbolic surface and then some infinitesimal deformation of it, and the infinitesimal deformation is uniformly contracting, which means that if you look at the length of all the closed geodesics on your surface, they decrease uniformly. Okay, so how do we construct uniformly contracting deformations of a hyperbolic surface? Well, there's one way, a kind of surgery method that was introduced by Thurston, which is called a strip deformation. So the idea is you take some geodesic arc, so some arc that goes from one end, one funnel of your surface into some other end, and then you take some other arc that's very close by here in this compact convex core, in the compact parts, but here, of course, it has to diverge at infinity. And then you take your hyperbolic scissors and you cut out the strip and you glue back. Hyperbolic geometry is really great because you can do all these procedures of like you take your scissors and you cut out things, you glue back things, and what you get at the end is still a hyperbolic surface. Isn't this fantastic? So I can do this, and when I do this, what I get is a new hyperbolic surface where all the geodesics that intersected transversely my little strip are now shorter. So this geodesic is shorter, and this geodesic is shorter. But not this one for the moment. But it doesn't matter, we can just do it again. So now we do it with another arc here, and the second arc, and we remove the strip, and what we get is here a new hyperbolic surface where this is also shorter and this is shorter. And so we just do this with enough strips on our surface, and at the end we get a shorter surface. So something that has been uniformly contracted. But so now what we want to do is not an actual deformation of the surface, but some infinitesimal deformation of the surface. So we just do this infinitesimally. So we pick some points on the arcs, and we decide these are the points where my strip is the most narrow, okay? And so then I do these deformations with removing strips, but I do it with narrower and narrower strips where the width of the strip decreases linearly, and I take a derivative of this deformation, and this gives me an infinitesimal deformation. Okay, I think you can believe me on this. Right, okay, so now the good thing is that in fact, any uniformly contracting infinitesimal deformation of a non-compact hyperbolic surface can be realized as a strip deformation. So you need to find the right arcs and strips, but if you find the right ones, then you can actually realize this deformation in a very concrete way with strips. And this completely, this gives you the crooked plane conjecture. So I'm not going to explain it in details, but essentially, once you know that it comes from a strip deformation, the strip deformation determines for you pairwise disjoint crooked planes. So how do we see this? So this is again the hyperbolic plane, H2, in the model of the hyperboloid. And each time that I have an arc alpha I in my surface that determines a strip, I can lift it to H2, like this, and this actually gives me a crooked plane. So you see that my geodesic already gives me the stem of the crooked plane, and now I just add the wings, and I get the crooked planes. So, so there's a real recipe, like if you give me a strip deformation, I give you crooked planes, and it gives me a tiling, an exotic tiling of R3. So, okay, so that's all for R3. And now, in the last few minutes, I would like to discuss something more general, namely higher dimension. So in dimension 3, we understand very well things are either essentially polycyclic or free group. But what can happen in higher dimension? So which groups can appear, which abstract groups can appear as symmetry groups of tilings of some Rn? So in fact, not only are there some polycyclic groups, but in fact, all the polycyclic groups can appear. That's nice, that's a result of Milner. All the finitely generated non-abelian free groups can appear. So not only in dimension 3, but there are constructions in higher dimension. But in fact, there are also more examples. So with two co-authors, we proved recently that, in fact, all right-angled Coxeter groups can appear. So what are these groups? So these groups are given by, here you have some generators, gamma 1 up to gamma k, and then some relations between the generators. And these relations, if I say in words what this means, it means the generators themselves are involutions, namely they're squared. If you square them, you get the identity. And then if you take two different generators, either they commute or there's no relation at all between them. And these groups appear in several areas of mathematics, and they are very nice groups. And in fact, what happens is that not only do all these groups appear as symmetry groups of tilings, but also all the groups that are almost right-angled Coxeter groups. And by almost, for those who know, I mean commensurable. Commensurable meaning they are the same up to passing to a finite index subgroup. And these groups, so there are all these groups with weird names like RAGs. RAGs means right-angled Artin group. And all these other groups with special names, but there are groups that people in doing geometric group theory like very much because they appear in many natural situations and geometric situations. Okay, so maybe I say just for the experts in 1 minute something a bit more precise about these right-angled Coxeter groups. So essentially, any right-angled Coxeter group, if it has k generators, then it can be realized as the symmetry group of an affine tiling of r to the power k minus 1 over 2 with non-compact tiles. And so where does this come from? Well, okay, so this is just written for the experts in the room, but essentially what I want to say is that you can do some kind of very similar construction to what we did in dimension 3 with the contracting deformations. So we had contracting deformations involving SO21 and the hyperbolic plane H2. And now in this higher dimensional situation, what we do is basically the same, except instead of having SO21, we have SOPQ for some P and Q that are more general than 2 and 1. And then instead of having the hyperbolic plane H2, we have some kind of pseudo-Riemannian analog of the hyperbolic space, which we called HPQ minus 1, and which is defined in the same way by just varying the signature. So I'm not going to expand on this, but I just wanted to include this slide in case some people are experts in this. And so now, of course, the natural question is, are there more groups? And my feeling is that, of course, there should be many more groups. We just need to find them, right? So now, as a conclusion, I would like to give you some open problems to show you that even though tilings are a very classical topic, Still, there are open questions, and it's the object of very active research currently. So essentially in this talk, I talked about 3 types of tilings. So the first type was the very, very classical one, so Euclidean tilings with compact tiles, right? And then I talked about something slightly more general, which was the affine tilings with compact tiles. And then at the end, I talked about even more general, which is the affine tilings with arbitrary tiles, where the tiles are allowed to be non-compact if I like. Okay, and so at each of these 3 levels, there are so many open questions. So for the very classical tilings, first of all, there's the question of the classification in higher dimension. I mean, I explained to you that up to dimension 6, it's completely classified, but I think already dimension 7, it is not fully classified. Then some other interesting thing that a number of people are working on is to do some kind of generalization where you want to replace Rn with something more general. And this more general thing is, in fact, some other simply connected nilpotent group. But if you don't know this, you can just forget. But just some people are working in generalizing the classical tilings. Then for the intermediate tilings, so we saw that the Auslander conjecture is still open, which says that all symmetry groups are essentially polycyclic. And then the question of classifying those tilings, even in small dimension, is open. So like in dimension 3, I believe some people know the classification, like Bill Goldman knows the classification, and it's partly written in his paper with Fried, but he always tells me that he would like to write down completely the details of the full classification because they're not yet written anywhere for dimension 3. So you can imagine that then dimension 4, it's not written at all. Okay, so, and then the last thing for the most general tilings. So first we would like to find more examples, as I said. Then we would like to find concrete descriptions of the tiles. So like in dimension 3, we had this description with the crooked planes, which was very nice. But in higher dimension, we do not have really crooked planes for the moment, so we would like maybe to find some analog. There's a question of how large can the symmetry group be. So if we look at tilings where the tiles are not compact, then the cohomological dimension of the group has to be smaller than the dimension n of Rn. But how much smaller? So in the examples of right-angle Coxeter groups that we construct, essentially the cohomological dimension is about the square root of the dimension n. But it would be interesting if one can find examples where this cohomological dimension is actually closer to n. It's still smaller than n, but closer. And then the last question is to describe the space of all possible tilings of Rn. So in dimension 3, we can describe all the tilings thanks to this description in terms of strip deformations. But in higher dimension, this is just widely open. And so I will stop here. Thank you very much.
¿Hay preguntas? Puede ser en español o en inglés. Sí, Alberto.
What about the hyperbolic tilings?
Sí, pregunta Alberto, ¿qué pasa con...?
Yeah, so this is a different theory.
Different theory.
Yeah. But yeah, one can do tilings of various geometric spaces, but today I decided to concentrate on affine Rn. Yes.
The space of all tilings is lamination?
Sorry?
The space of all tilings is a lamination, like in a two-dimensional case?
The space of the space of all in Euclidean two-dimensional.
That's a lamination.
Yes.
Is it higher dimension also?
Yeah. I don't know.
¿Más preguntas? Bueno, pues si no hay más preguntas, muchas gracias.
So, if some of you want to see the objects, you can come.
Can you put it back together again? Can you put it back together again?
Yeah, yeah.
Because I'm afraid